Thank you very much. Thank you for the introduction, and especially thank you for the invitation to speak. I would very much have liked to be there in Santa Barbara to participate in discussions and do everything live. I had a prior commitment, which has me today in Africa. So I am here in Ghana at this international school on the frontiers of light. And so I'm on this beautiful tropical campus, almost at the equator. I have these students who are fantastically interested and fantastically earnest. It's a very different experience than teaching in Europe. But unfortunately, it means that I am here because this was a prior commitment. Okay, so today I'm going to be talking about work that is described in these three papers. So the first two were the thesis contents of Silvana Palacios, who was a PhD student and then a postdoc with me. And the third is by Pau Gomez, who was also a PhD student, all of them working on the ultracold experiments. Okay, so I'm talking about magnetic field sensing at a meeting on physics beyond the standard model. Why talk about magnetic field sensing? Well, because there are a number of experiments that look just like magnetometry experiments where there is some source which is to be detected by some collection of atoms which are prepared in some way to maximize coherence and to maximize sensitivity. And so I think there is probably something to be learned from the large experience with magnetometry when doing these kinds of searches for physics beyond the standard model. And in particular, I'm going to focus on this expression, which is often described as the quantum limit of sensitivity for a magnetometry experiment, where the uncertainty in the magnetic field is related to the gyromagnetic ratio, the number of atoms that are being used in the sensor, the coherence time T2, and the duration of the measurement. And this is often described as equation 1 because it often is equation 1 in magnetometry experiments to describe what should be possible with the technology that is being described. At the same time, it's an expression that is almost never tested. And so you would not be crazy to doubt its validity. Okay, why might you doubt its validity? Well, I'm going to give you some reasons and then try to explain what I think is correct and what is not correct about equation 1. So this is from the first paper, the Reviews of Modern Physics from 2020. And what we've done is we looked up a great number of experimental results on sensitivity, and so the sensitivity is on the vertical axis here, and the effective volume, which I'll explain in a second, is on this other axis. And you see that there is some kind of regularity in the best results over many orders of magnitude. Yeah. Okay. To be clear about what's being presented here, these are only experimental sensitivities that have been measured and reported. There are no projections here. There are no predictions about what the technology should be able to do with a few improvements. In order to limit the amount of work in researching this, it is limited to DC fields, so that's things which are below 1 kilohertz, except nitrogen vacancy center and diamond is almost exclusively used for radio frequency sensing, and it's such an important technology that we wanted to include that. And so all of these things that look like a diamond with radio, those are radio frequency with diamond. Okay. And then there are several other technologies that are represented here at the same time. And then you might ask, how do I get an effective volume for a planar sensor like a squid? And so that's simple. Use the fact that the field is not going to change abruptly as I go out of the plane. And so I say the effective volume is the 3/2 power of the area. And for point-like sensors, I identify the point of closest approach and take the volume of a sphere that has that radius. And so this applies, for example, to the single nitrogen vacancy center experiments. It was a lot of work. It was a chore to look all of these things up and to generate the graph. I'll leave this up for a minute in case anybody wants to take notes. I can't hear if you're laughing or not, so I will just assume that that was hilariously funny. Okay. So then what is this regularity that I mentioned before? This green line is an energy resolution per bandwidth of h bar. So what is the energy resolution per bandwidth? That's a figure of merit that combines the mean squared error on the field measurement, the volume of the sensed field, the time that was used to make the measurement, and some constants. Okay? And this is simply a way of, one way to think of this is this is simply a fair way of comparing fast measurements and slow measurements, and the fact that if you have a bunch of fast, poor measurements, you can average them to get something which is equivalent to a slow, good measurement. And the same fair comparison is applied for the volume. If you're trying to measure the field in some large volume, you could use a large magnetometer, or you could use several small magnetometers and average them. And assuming that those are independent, have independent noise, then the fair comparison will be this. And then you divide by 2 mu naught in order to give it units of action, and you have the energy resolution per bandwidth. Okay. Then if you look at what had been accomplished up to 2020, then there were several technologies that had come close. So the single nitrogen vacancy centers got 2.5 h bar, squids got 2 h bars. There's a BEC experiment by Dan Stamper-Kern that got 1.25 h bar, and atomic vapors had 44 h bar, but it should be noted that those highest sensitivity experiments were limited by their shield noise, and so that's not necessarily a limitation of the sensor itself. So you look at all of this and you say, okay, there seems to be something about energy resolution per bandwidth is h bar. And then if you compare that against the equation 1 sensitivity, then you find that for any of these atomic vapor sensors, then the equation 1 sensitivity is a couple orders of magnitude below. Okay, so I think that that was the question that we wanted to understand in doing the study. Is there something there beyond equation 1, or can we just trust equation 1 for these things? Okay. I just want to point out that there's a big difference between this and the quantum limits that we're used to thinking of. So this is a limit which is defined by the volume, and that's the volume of the field that's being sensed, the time, so that's the duration that you're sensing it. So in particular, if you had a transient event, then that might be all the access to this field that you could have. And thus, this is a limit which is defined by the quantity that's being measured and not by the sensor that is measuring it. Okay. It's very different from quantum metrology. In quantum metrology, then we always have either the standard quantum limit scaling as 1 over square root of n, or Heisenberg limit scaling as 1 over n, and then there's some scale factor which might be the wavelength of light in an interferometer, or frequency in some kind of atomic physics experiment. Okay, and that is a forgiving kind of limit because there's a way to get more. You can invest more particles, or you can change the scale factor. And when there is this kind of limit, then it's an unforgiving limit. There's no resource in here that you can spend more of, and the scale factors are fundamental constants. Okay, so it's not just a phenomenological observation that sensors up till 2020 had not beaten this. There are good quantum noise models that describe why some of these sensors should not be able to do this. The first is from 1977, this paper by Tesh and Clark, which is very well known in the squid field. And they describe how the noise, in this case in flux, gives them a sensitivity which was originally, so this is the power spectral density for the flux divided by 2 times the effective inductance of the squid. And in the original paper, they had 1 quantum noise model, and this gave pi h bar. And then in their next paper, 4 years later, then they changed their quantum noise model, and that pi disappeared, and this became h bar. Okay. And so that doesn't look immediately like the energy resolution limit that I showed. It's got flux, it's got this induction in it. But when you consider the relationship between between inductance and geometry and flux in a squid, then you see the inductance is related to the square root of the area, the magnetic constant, and alpha, which is a dimensionless factor, which arises from a difficult calculation of exactly how the field distributes around this branching ring. But this is something of order 1. And so this Tesh and Clark limit then becomes this. If you want to compare it against volumetric sensors, that's straightforward if you associate the 3/2 power of the area with the volume. Okay, so it was already in 1981 that squids reached this limit. So I would take that as a serious limit. Unless squids are operated in some different way than they traditionally are, then you should consider that a solid limit for squids. Okay, spin precession sensors. So I think this is familiar, so I won't take very long for this. If I take the equation 1 sensitivity and I square that and I multiply by the volume of the field that I'm measuring and I divide by 2 mu naught, then I get the energy resolution and a lower bound on it. And that contains the inverse of the density here, and it contains the relaxation rate, and those are not independent. But if I go to high density, then I will see a 2-body relaxation. And so this relaxation rate is lower bounded by that 2-body relaxation. And that gives me now a number independent quantum noise limit. And that is what you should expect for a spin precession sensor that has been optimized. Okay, so if you look at this ratio of a 2-body effect, that's something that has to do with 2-body relaxation and a 1-body property, which is the gyromagnetic ratio, then those are not independent in immobilized spin sensors. But basically, the fact that these spins can couple to the magnetic field means they couple to each other by an amount that makes those things proportional to each other. Okay, so I won't talk about it much here, but we have a paper on this that does a quantum mechanical analysis of this. I illustrate this with a classical model. So you can see a bunch of spins which are initially prepared orthogonal to the magnetic field. And as I let them go, then they're precessing mostly around their neighbors, but partly around the field, and it gives a nice free induction decay. And that free induction decay does, in fact, have a decay rate which is proportional to the square of the gyromagnetic ratio, which means that we get an energy resolution that has the expected dependence for this energy resolution limit. And then we do a Monte Carlo simulation, and we can get a number for the prefactor, which is about 1/2 for DC magnetometry and about 1/4 for RF magnetometry, so not very different. Okay, so I would also take this seriously, although there are good ideas out there for dynamical decoupling of the dipole-dipole coupling through pulse sequences, and that's not something that's considered in my analysis. So that may be able to push beyond this limit. Okay, and then where there really is an opportunity is in gaseous or potentially liquid systems, where this single atom property, the gyromagnetic ratio, and this 2-atom property are really coming from different physics. This is atomic physics and this is molecular physics, and so you don't expect those to be strongly coupled to each other. Nonetheless, if you look at rubidium-87, which is our favorite atom for making magnetometers, it turns out, I would say accidentally, that ratio is in fact about 1, and so the 3 sensors that we know the most about all obey an energy resolution limit like this, with the energy resolution being about h-bar. Okay. Then the fun part of writing this review article was to look at possible explanations that might be across all different technologies. So I think of this as we have model-dependent predictions that all seem to agree and all are different in their mechanism, is it possible that they're all looking at different manifestations of the same thing? And so we looked at quantum metrology limits already mentioned, energy time uncertainty relation, quantum speed limits, entropy limits, limits that are based on quantum amplification. None of those does the job. They don't even have the right form. So the energy goes as the square of the field, and the energy resolution goes as the square of the, this uncertainty relation would concern the uncertainty of the square of the field, whereas what we have in the energy resolution per bandwidth is the mean squared error. So it's not even the right quantity for this first line. And then the back reaction to the quantum noise of a magnetic spin system, that's an interesting explanation. It gives the right answer if you do the calculation uncautiously. Same for vacuum fluctuations. You can convince yourself that the energy resolution limit of h bar should come from vacuum fluctuations. I don't believe either of those, but the explanation would have to be either in a question or in the article here. Okay, so having found no technology independent limit, then that opens up possibilities for a number of non-traditional technologies. Bose-Einstein condensates are what we know how to do, but there are many other things here which would evade one mechanism or another. So I encourage people to censor people to go after these kinds of technologies. Okay, so let me tell you a little bit about the BEC magnetometer. So I think of this as a rich man's atomic vapor cell. So we collect rubidium-87, we hold it in an optical dipole trap, we do optical pumping on it prior to condensation, and so we get a polarized ensemble. We do Faraday rotation probing, so we have a non-destructive measurement of it. And this is great for magnetometry because it gives a strong spin polarization, large ferromagnetic ratio, strong optical transitions to probe on, and it escapes most of the bad things about working with a vapor cell. In particular, it's not sensitive to gradients. There are no walls, diffusion, and as I will show you, there are no depolarizing collisions, and other effects are weak. So it makes it a very attractive system for fundamental magnetometry. The reason that it doesn't have depolarizing collisions is basically due to lack of entropy. So when you go through the BEC transition, then you go from having a thermal cloud with a lot of entropy into it to having a pure BEC, which does not have that entropy in the center of mass degrees of freedom. So you lose the usual reservoir for collisional depolarization. Okay. To check that, we did a simple experiment where we polarized the atoms, allowed them to precess, and then do a readout after some period of time. It's basically a T2 measurement. And what we see is an exponential decay with a T2 time of 7.7 seconds, which is exactly what we see on the decay of the atom number. So we're directly seeing that there is no depolarization in the system over as long as we can measure. Okay, so if I take that T2 time and the number of atoms and the volume of the condensate from the Thomas Fermi approximation and understanding of the trap, then I get an equation 1 energy resolution per bandwidth of 0.01, which is to say there should be a point here. Okay, so again, that point doesn't get to go on the graph because it's not a measured number. It's in some sense a predicted number. Why not measure it? Well, there's a problem with that. It would require very good shielding. Good shielding has been made by the group in Trento, but it's not nearly good enough. So if you look at the noise of low noise ferrite magnetic shield, then due to 1 over F noise at these low frequencies, you get something like this. And in our case, the frequency is a fraction of a hertz. And so that's far beyond our sensitivity. So even good shielding, good room temperature shielding would not do that. So I'm not interested in doing a cryogenic atom trap. And so that's as far as we could go with the experiment at that point. it is nonetheless possible to use what we know about BEC physics to get a number for this. What we do is we describe a protocol where the spins are polarized, tipped by a radio frequency pulse onto the equator, allowed to precess many thousands of times in the presence of a magnetic field, and then non-destructively read out by the Faraday rotation probing. We study that a couple of ways. The first is just a Gross-Pitievsky equation to check and justify the single mode approximation. And we find that the deviation in the GPE simulations is equivalent to about 1 spin. So that's at the quantum noise level. So that's, I think, acceptable. And then within the single mode approximation, we have a competition of 3 different effects. The linear Zeeman shift can be ignored by going to a rotating frame, and that leaves just the ferromagnetic and quadratic Zeeman shifts to worry about. And the quadratic shift is simple. We're in the F=1 ground state, so it's in some sense just 1 energy difference. The collision effects are also very simple. For the systems, it just means that I can take 2 m=0 atoms and they collide to become 1 m=-1 and 1 m++. But those 2 effects don't play well together, and they cause a shearing, and that shearing can be treated by the truncated Wigner approximation. So this is something that was actually suggested to me many years ago by Anna Maria Ray. Thank you for the suggestion. And that's a quantum optics technique. We learned it in detail from this thesis by Bogdan Apunchuk. What it allows you to do is include all of the relaxation effects as well as the nonlinear couplings into a single equation, which, as usual in quantum optics, means a stochastic differential equation that reproduces the quantum statistics. Okay, so when we do that, so this is now after precession. So this is before precession, this is after precession by 1 second. The scale has been magnified by a factor of 10 to make things visible. Then if we do this at a relatively strong field, then we see a shearing which hurts our sensitivity because it broadens the spins in the direction that they're precessing, which is to say it makes the precession angle more noisy. And when we reduce the magnetic field in the simulation, however, then the ferromagnetic interaction is holding this distribution together, and we get something which can be close to quantum noise limited. Okay, so put that a different way, as a function of precession time, if we include just the projection noise, then we get this brown curve. If we include 3 body losses, we don't get a large correction to that. At the trap pressure that we have, 1 body losses are a much more significant effect. And if the field is too strong, then the quadratic Zeeman shifts give us this shearing and eventually worse things. But there's no reason we can't work at much lower fields than this. And so this level here is the appropriate level for the spin noise. And then there's a readout noise because we're not yet quantum noise limited. And so that brings us up to 0.7 h-bar. And so that allows us to put a point, which here is part theory, part experiment, but it's backed up by the quantum statistical theory of BECs. And so we think it's pretty trustworthy at this point. Okay. That's we've been in a race with the people who are doing nano ferromagnets. So this includes Derek Jackson-Kimball, Alexei Shuskov, and Dmitry Budker, who I believe were the first to propose this as a technique. Hendrik Ulbricht's group recently reported at the EPS Condensed Matter conference in September. They reported a number. I show their slide here, and so they are reporting in a preliminary way this. So it seems like the line has been crossed twice now, and I think that's encouraging for all of these techniques.
5 minutes?
5 minutes, great. Okay, so then let me say a little bit about the potential as a comagnetometer. We what good is a magnetometer if it's better than the best shielding that you can put it in? It will just detect noise. Well, that's not true if you make it into a co-magnetometer, and so that's what we've looked at in this paper. So the method here is to make one magnetometer from the f=1 states, one from the f=2 states, and since they're made in the same trap, then they are sensing the same volume. They precess in opposite directions because of the different gyromagnetic ratios, and they can be independently probed because of the hyperfine splitting here. We can tune a laser to probe one and then shortly after probe the other and get a precession angle for each one. And that's interesting as a co-magnetometer because the f=1s have anti-parallel nucleus and electron spins, and the f=2 have them parallel, so any effect that is on the nucleus as opposed to the electron or affects them in different ratio would be detected in the relative angles of the two components here. Okay, so in the interest of time, I won't talk about an interesting condensed matter effect here, but suffice it to say that the co-magnetometer works. And then what could you do with this as a detector for new forces? So prepare a condensate, use radio frequency and microwave manipulations to prepare the superposition, allow it to precess in the presence of the magnetic field that you're applying and whatever exotic effect you're trying to measure, and then read out. Because it's a condensate inside an optical trap, you could get an object to a distance of about 100 microns. The size of these beams is a beam waist of 50 microns. So take that as an order of magnitude number for the closest approach. Okay, and then if you calculate using methods that I learned in this beautiful review article, then you can calculate its sensitivity to the monopole dipole coupling and compare it against other reported results. So rubidium-87 has a valence proton, so we're in this graph and not that graph, which is nice because there are fewer results in here. And also we're talking about 100 micron length scales. So we're down in this part of the exclusion curves where there are not many results. Okay. And so when we do that calculation, assuming the sensitivity that I inferred before from the theoretical calculation of 70 femtotesla per root hertz, averaging for 1 week of running, then we get a statistical sensitivity, which in response to a centimeter scale tungsten mass, which is 100 microns away, you get this orange curve, and in response to the Earth, then you get the Earth at a couple of meters distance, then you get this purple curve. So it looks like it has an interesting statistical sensitivity, which derives from its unique properties as an ultracold medium, an ultracold sensor, and we are starting to look at systematic effects to understand if it makes sense as a real sensor. Okay. So in conclusion, this energy resolution limit really is a magnetic sensitivity limit for the best known, best studied technologies that we have as they are currently used. And state-of-the-art sensors are close to reaching this limit. It does not appear to be anything fundamental, and so alternative technologies can pass this limit, and that includes spinor condensates, levitated particles, and other things. And I think that spinor condensates may be interesting for detecting new spin-dependent forces. So I thank you all for your attention. I thank the people who contributed to this, who are many, and I'm eager to hear your questions.
Thank you so much. So thank you for this very interesting talk. It's really interesting, just fantastic collection of everything. It must have taken enormous amount of time, and yes, we did laugh at the suggestion of taking notes.
Thank you. Yes, I agree with Mariana. Very, very nice talk. I have one question on the validity of the single mode approximation. I imagine would depend on the temperature, the number of particles. So when you were saying that it's valid up to one atom in the variance, what conditions were you assuming?
Yeah, that's assuming that it starts as a pure condensate.
All the atoms in the t equal to 0.
Right.
Okay, so but I imagine that then for realistic condition, experimental conditions, maybe that's not satisfied, and because also depend on the number of particles because of quantum depletion. Yes.
Yes, it's not a high density condensate at all, and in fact, its coherence properties get better as it gets lower density. So I'm not sure how important the depletion is going to be, but I appreciate your point about the thermal fraction, and that's of course, not something that we know very precisely.
Okay, great.
Other questions?
I think Alice has a question.
I just wanted to somehow react to Ana Maria's questions. I wanted to say that if needed, one can, of course, in the truncated Wigner approach, put in addition to the quantum fluctuations, the initial thermal fluctuations, and then one would have the equivalent of a classical field with a quantum fluctuation, which allows you to describe the squeezing, and also with initial finite temperature if needed. Just a comment.
Thanks for a really nice talk. It's interesting to see that these sort of controversies or questions about the energy resolution quantum limit have not gone away for so long. Do you have any intuition for what's needed to actually beat this not really a limit? So you have examples of things that can, outperform it, but is there some secret sauce or essential ingredient there?
Well, I didn't say very much about that slide. I think there is not a unified reason why there is a limit. I think it's really an accident that squids and immobilized spin precession sensors have the same value and have the same value as rubidium. Then because it's actually a few different limits that are specific to specific technologies, I think in squids, it's very natural now. I didn't say much about squids, but part of the reason that DC squids have this limit is because they introduced relaxation in order to make them non-hysteretic, which in the 1980s was probably an important consideration. But if you're able to make superconducting qubits, then you'll have some initialization mechanism, and you don't need to introduce relaxation in order to make them non-hysteretic. And so squids can beat it that way. Working with helium-3 should be a fantastic way to beat it, because then the collisional effects are very weak. The gyromagnetic ratio is small, but the collisional relaxation is much smaller. And so working with nuclear spin ensembles, I think, is a good way to do it. And there seems to be a lot of people that are excited about these nano ferromagnets. I'm not an expert in that, so I only know that good people are working on this.
Thanks.
Other questions?
Hi, I'm James Gardner from ANU. I wanted to ask, so if this energetic limit isn't the fundamental limit, do you expect that the equation 1 sensitivity will be eventually reached? You said it was several orders of magnitude, the current line that you were showing.
That's another question. I sort of expect that equation 1 could be reached if you had better shielding, or potentially if you had a smaller number of atoms in your system. it's a bit hard to imagine a system which, when optimized, would have a small number of atoms. I don't know if you can hear that, but we've got thunder here. But yes, you could imagine taking a reasonably small sensor and putting it in a very good shielded room and then testing that. I'm all, for other reasons, for quantum optical reasons, I'm not convinced that equation 1 is going to hold when you take into account things like spin squeezing. But that's a different discussion.
Okay, thank you.
Thank you. Other questions? Do you have any questions from anyone on Zoom? So you can just unmute yourself and ask a question. Does not look like it. Well then, thank you so much for a very interesting talk, and I guess thank you for you and Elena for the wonderful session.